or get better. Okay. So I may have to look at I want to check my audio. I may have to look at the board because I obviously haven't rehearsed. Testing, 1, 2, 3. Does anyone need one? All right. I'm not dressed appropriately for a professional presentation, but then again, no one is here today, so we're okay. Oh, that's true. I should say no one. I just say that wasn't a criteria. Okay. Good morning. My name is Jeff Lacombe, and I'm going to talk to you a little bit about a research project that's been many years in the making, but only recently that we've been pursuing this kind of research formally. I've been collaborating with Professor Wong here in the mechanical engineering department, since about 2002 or so on aspects relating to robotics and aerospace technologies, and for a variety of reasons not really relevant here. But this led us to interest in developing autonomous parachute systems. The idea here is that when you are trying to put a package down onto the ground, maybe on Earth, maybe on another planet for that matter, in many situations you want to get it as accurately to that spot as you can. And in many situations you don't have a human parachutist to guide it down, to fly it down to that spot. A case in point would be to try to land the Mars rovers into a particular spot, onto a particular valley floor or something like that on the surface of another planet as accurately as possible, because that's a scientifically interesting spot. Other applications would be, for example, trying to deliver supplies to military forces who are dug in on a mountaintop someplace or along those lines, and you need to get them supplies or you need to get them equipment. Maybe you need to deliver relief supplies to a refugee camp in Africa or something to that effect. The idea here is that in many situations you want to get something accurately to a spot on the ground. Now, there are many people doing research in this area nowadays, and for the most part the cutting edge is pursuing autonomous parafoils. These are things that are very flyable, very directable. They have thrust in a forward direction. They don't just come straight down or anything like that. However, they tend to be very complicated and expensive, and these are leading to, I guess we could call them stumbling blocks along the way of getting the technology to work reliably. And we came up with the idea of maybe not getting all of the functionality of an autonomous parafoil, but getting some of it by making a really simple system that simply takes advantage of the wind. Okay? If you know what the wind is at all altitudes, and it's not the same, it varies in direction and speed with altitude. If you know that information ahead of time, you can use it to plan your path and trust that the wind will simply take you where you want to go. Okay? So, topic why, what we do. Okay, so the process that we do, that we use to study this is to, first of all, we need to gather our wind data. And we have a student working on technologies for dropping what we call dropsons out of an airplane. It's a cheap, small, inexpensive thing that measures the wind speed and then radios it back up to the airplane while it's still falling. And then soon after we throw that out the window, out the back, out the door, whatever, we throw our main payload that has a control system. It's an electromechanical system that simply reels in the parachute and causes the parachute size to change. So when we first release it, the parachute might look something like this. Fairly large, and we have our payload box all down in here. Inside the box we have the equivalent of a fishing reel, where we can reel in these lines and we cause the parachute to get a whole lot smaller. It kind of forms a much taller but narrower profile where this dimension is much smaller here than over there. And as you might imagine, just simple aerodynamics would suggest that these are going to have very different descent rates because of their aerodynamic cross-section. Okay? That's the crux of our system. We want to change the parachute size so that we can plunge through the air layers that have unfavorable wind speeds and wind directions as fast as possible. Spend as little amount of time as we can in the bad wind layers and slow down, make it really big, slow down to spend as much time as we can in the layers that are taking us in a direction that we want to go. Right? Because remember, the wind direction and wind speed is changing as you come down through the atmosphere. Okay? So the key here is you need to know the wind speed and direction ahead of time. And we are just trying to make a simple system that can take advantage of this information and glide and go with the flow, as we would say, as much as possible. So we do a fair amount of modeling of the physics. And the physics modeling is very simple. We do a layer by layer calculation in the air column. So let's say our wind speed varies with altitude. And it's also going to vary, the direction is going to vary with altitude. We will break our entire mission down into altitude layers, and we will calculate ahead of time what trim configuration we want to have in which altitude layer. And then we have an onboard computer that does the physical modeling of this. It plans ahead where it needs to issue the commands to change the parachute size. And then as it's going down, it's judging its actual position compared to, there's 5 minutes, compared to where it actually wanted to be. We do experimental measurements by making these systems. We throw them out of the back of an airplane, and we go and chase them, we go and find them. They land somewhere out in the desert. And we log all this information while we're on our way down, and we draw comparisons with how well it should have performed. When things go well, when we have good wind data that's recent and local, we can land typically within about 50 feet of where we're aiming when we drop from an altitude of 30,000 feet is pretty typical. That's way higher than most skydivers will drop from. That would be considered a high altitude payload drop. Military does that, no one else really. But we also do experiments up to over 100,000 feet in altitude, and that would be geared towards simulating like Mars payload deployments and things like that. So we're doing pretty well with the work. We're progressing. We've been working on this formally for about 2 or 3 years now. We've had a couple of papers presented in these areas. Some of the criticisms that we're getting are that, this is too simple, it's too easy. Everyone's working with these complicated parafoil systems, and they're getting accuracies down to 15 feet rather than 50 feet, 1.5 versus 5.0. I can walk 50 feet to go get my stuff. That's sort of our attitude, and we are working to convince the rest of the community that the low cost and simplicity of this is enough to compensate for the loss of those 45 feet of potential accuracy. So that's it. So. All right, he did it in 6:46. Oh, not good, not good. I didn't prepare enough.